In this video, let's solve problems on units and measurements. Now let's start with this. Answer true or false to the following questions. So I have questions A to G. Yeah. Now let's answer true or false for the questions. Now the first one. The first question. A. Both a spring balance and a chemical balance are used to measure the mass of an object. Now, in previous videos, we have talked about spring balance, chemical balance, and difference between mass and weight. But now, let me start with mass. You can note points here. So, mass. Mass is the quantity of matter in a body. Mass is the quantity of matter in a body. Now, other information you need to know about mass. Now, it is consistent everywhere in the universe. It means mass is constant anywhere in the universe. Mass will not change. Mass will remain the same everywhere in the universe. Take note. Another point, it is a fundamental quantity because mass is measured in kilogram, so and it is a fundamental quantity. Another point, its SI unit is kilogram, like I stated here. So that means mass is a quantity while kilogram is units. So the SI unit is kilogram, and we said SI unit are those units that is accepted generally. So another point, it is also a scalar quantity. It has only magnitude but no direction. Another point on mass, note all these points, can jot it. It is measured using a balance, of which there are various types, such as chemical balance, beam balance, lever balance, and direct reading balance. Direct reading balance. Now, these are the instruments we can use to measure mass. So, chemical balance, beam balance, lever balance, and direct reading balance. Now, let's talk about weights before we now go back to the question. Now, let's see weight. So, weights. Now, weight is the force or pull with which the earth attracts a body towards the center of the earth. So, weight usually acts downward. Note points under weight too so that you can jot it also. It varies from place to place on or around the earth's surface. That means weight varies, is not constant like mass. So it varies from place to place. So take notes. That is, it changes from place to place. Now, it is a derived quantity because weight is a kind of force. Weight is a kind of force. So, force is in Newton. And what is force or weight itself is mass times gravity. mass is kilogram, gravity is meter per second square. So that means the units here is derived units. So likewise, weight will now be a derived quantity. So weight is a derived quantity. Another point, its SI unit is Newton. So SI unit is Newton, or kilogram meter per second square, in which we call Newton. It is another point, it is a vector quantity. It means it has both magnitude, it has length, and it also has direction. Another point, it is measured using a spring balance. It is measured using a spring balance. Spring balance. Take note. Now let's go back to the question. So the A part now says both a spring balance and a chemical balance are used to measure the mass of an object. So the A now, as we can see in mass and weight, you see where we say mass, to measure mass, that we can use chemical balance, we can use a beam balance, we can use a lever balance, and we can use direct reading balance. While weight, we can use spring balance. That means both a spring balance and a chemical balance are not used to measure mass. Now the only one that is used to measure mass here is the chemical balance. So that means the chemical balance is used to measure mass, while the spring balance is used to measure weight. That means this first one is false, so it's not true. So as only as spring balance is used to measure weight, while chemical balance is used to measure mass. So like that. So the statement is false. Now B, either may be used to measure weight. Either may be used to measure the weight. Still the same as the first one, since the two of them cannot be used to measure mass. As we have said, spring balance is used to measure weight, while chemical balance is used to measure mass. Spring balance and chemical balance cannot be used to measure only mass. So spring goes with weight, while chemical goes with mass. So that means the B part is also false. So either may be used to measure the weight. So it is only spring balance that can be used to measure the weight. So chemical balance is used to measure mass. So B is also false. Just like the A, it is only chemical balance that we can use to measure mass. So we can't use spring balance. Spring balance is used to measure weight. Now the C, Hooke's law forms the basis of operation of the spring balance. Now that is true. So the extension of a spring is directly proportional to the weight of the body. So that is F is equals to KE. So this is according to Hooke's law. So that means the statement is true. For C parts, it is true. That is, Hooke's law forms the basis of operation of spring balance because there is extension there and force constant K. So that one is true. D, the chemical balance works on the principle of moments. Now, the chemical balance, when we say balance, it means like left hand side should balance the right hand side. So this is also true. That is, this involves two bodies and a lever. So that means it is also true. And we said out of the instruments we use to measure mass, we already said that we can use a lever balance. So that means the statement is true. The chemical balance the chemical balance works on the principle of moment. So that means to measure the mass. So it's true. So the statement is true. Now F, which we are in D now. Now, if the acceleration due to gravity changes, the reading of the spring balance will change, but that of chemical balance will not. Now, to understand this better, if the acceleration due to gravity g, if g changes, the reading of the spring balance will change, but that of chemical balance will not. We already said that we use spring balance to measure weight, and we use chemical balance to measure mass. And part of the points stated in weight, we said weights can change from place to place, but mass remain the same in the universe. So now, according to this, we can see that the statement is true, because if the acceleration due to gravity changes, the reading of spring balance will change, meaning weights can change from place to place depend on your acceleration due to gravity. So that means it can change, but that of chemical balance will not change, because no matter what, mass never change, and we use chemical balance to measure mass, so that one will remain the same. So that means the statement is true. If the acceleration due to gravity changes, the reading of spring balance will change, true, but that of chemical balance will not, true. So that means the statement is true. Now F, a micrometer screw gauge. F now. So a micrometer screw gauge can be used to measure the internal diameter of a tube. Now, if we check our point on micrometer screw gauge, we can only use micrometer screw gauge to measure the external diameter. So that means this one given in this F is best used for vernier calipers. That is, vernier calipers can be used to measure internal diameter of a tube, but not micrometer screw gauge. Can go back to the video of vernier and micrometer to understand better. So that means this F is false, as it is vernier calipers that we can use to measure internal diameter of a tube, not micrometer screw gauge. So it is false. Now G, for a ruler graduated only in centimeters, measurement can be made accurately to the nearest millimeter. Now the statement here is false. R is a false. Let's see, for a ruler graduated only in centimeter, that means such ruler will look like this. So such ruler will look like this. So graduated in centimeter only. So I want to extend it. So now, if it's graduated in centimeters only, that means I've discussed this too under accuracy error analysis. Now this one will be like 0, 1. That means it's measured in centimeter only. No calibration, no centimeter marks. Yeah, that means it's only in centimeter. 7. So that means there is no calibration like 1 2 3 1 2 3 1 2, no calibration here. So that means this ruler measures only in centimeter. So for a ruler graduated only in centimeters, so as shown, measurements can be made accurately to the nearest millimeter. Let's say the precision, so it can be measured to the nearest millimeter. So to the nearest millimeter is like 1 millimeter, and this case this is measured in centimeter. So that means according to this, the ruler is graduated in centimeter, so it can measure accurately to 1 centimeter. So because the smallest graduation here will be 1 centimeter, so in this case there is no calibration, so there is no how we can measure with a certain decimal point. So no how we can measure to a certain decimal point since there is no calibration. So now this ruler can only measure based on what they described, that for a ruler graduated only in centimeters, measurements can be made accurately to the nearest millimeter. So that, but here the reading accuracy of this ruler can be 1 centimeter, and this can measure up to half of the smallest graduation. If you watch the first video on measurements, so reading accuracy of a meter rule is the smallest half the smallest graduation. And since the smallest graduation of this meter rule as described in this question is just 1 centimeter, that means the reading accuracy here will be 0.5 centimeter. So now this 0.5 centimeter, change it to millimeter. If you multiply by 10, that is 5 millimeter. Now this is not to the nearest millimeter, so this is 5 millimeters. So that means the precision here is limited to 1/2, that is half of the smallest division of the ruler. So that means the statement here is false, cannot be true. So, and take note of this, they say only this ruler is graduated only in centimeter. That means it can only be measured to accurately to 1 centimeter, and the reading accuracy is half of the smallest division, and that is 0.5 centimeter, which can be 5 millimeter. So that means the statement is wrong, cannot be measured to the nearest millimeter. So this is all for this question. Now let's see another question. Yeah. Now this is another question. In the following list, the unit of each quantity is indicated in brackets. Answer true if the indicated unit is correct, and false if it is incorrect. A. Work. So the A part, work is equals to force times displacement. And what is force? As in work done is force times displacement, or force times perpendicular distance. So work done, we can split work and force further to get mass times acceleration times displacement. Now the units for mass, so work done can be, the unit for mass is kilogram, times the unit for acceleration. So acceleration is velocity over time times displacement. That means work done is kilogram times velocity is in meter per second, then per second. So that will be meter per second square. That means the unit for mass is in kilogram. The unit for acceleration is meter per second square. The unit for displacement is meter. So combine the three. So times meter. So how many meter do we have here now? So meter raised to power 1 over another meter raised to power 1. So work done is kilogram meter square per second square. But if you look at the way they write it there, they write it as kilogram meter square per second square. That is, this s raised to power, this is 1 over s square, which is s raised to power minus 2. So that means if you compare the units here, then the statement is true, as in our result is the same as this. So that means the statement here is true. So A part is true. So A is true. Now let's say the B. B is power. What is power? Power is work over time. So B part, power is work over time, and the unit of work can be joule or Newton meter. So joule time is in second. That means this can be joule s raised to power minus 1 or joule per second. Now if you compare with the results there in B, it is joule second instead of it to be joule per second. That means it is force. So the B is force. B is force. Now C, gravitational potential. Gravitational potential. We represent gravitational potential as V. So gravitational potential is the, or let's say gravitational potential energy is the energy possessed to acquire by an object due to a change in its position when it is present in a gravitational field. So if, like, we know that objects that has mass attract each other. So that means if I have a ball, let's say I have a ball here, a ball of mass m. Now there will be a gravitational field around it. Now if I have a small mass here also, now this small mass will be attracted to this big mass, and that is your gravitational force. You can have the idea from gravitational force. Now what is a gravitational force? If you remember, So we can say, let me brief, like the universe has a lot of, I want to explain gravitational potential better so you can get the concept. So the universe has a lot of forces, a lot of pushes and pulls. We are always pushing or pulling something, even if it is only on the ground. But it turns out that in physics, there are really only four fundamental forces from which everything else is derived: the strong force, the weak force, and the electromagnetic force and the gravitational force. Now, the one I want to talk about is the gravitational force. Is the gravitational force. The gravitational force is that force, or is a force of attraction, or the gravitational force is a force that attracts any two objects with mass. So if any two objects should have mass, the gravitational force will attract the two bodies. So that's why I said the gravitational force is a force that attracts any two objects with mass. So we call the gravitational force attractive force because it always tries to pull masses together. It never pushes them apart. So in fact, every object, including you yourself, so every object is pulling on every other object. So I'm using human being too as example. So human being too is part of those objects. So every object is pulling on every other object in the entire universe. So this is called Newton's universal law of gravitation. So admittedly now you don't have a very large mass, and so you are not pulling on those other objects much. That's why we are not really feeling the pull. So an object that's really far apart, meaning if it's far, so to each other or from each other, don't pull on each other noticeably like that. But the force is there and we can calculate it. That is, the force of attraction is there. We can also calculate it. So now, but the gravitational potential now is that potential energy possessed or acquired by an object due to change in its position when it is present in a gravitational field. So like I said, if I have a ball of mass m, now this ball, you have a gravitational field around it, as in everywhere around there. So now if I have another small ball present in that gravitational field, let's call this small m. Now if I change the position of this ball, let's call this first position a. Now let's say I change the position to point b, from A to B. That means I will have applied a kind of energy or a kind of force, because this small ball here will be attracted by this other ball here, so it tends to be moving towards this direction. But now I'm forcing it to come towards this direction. That means I must have applied a kind of force. So now, and the energy I use on this ball is not wasted. The energy is stored inside that ball, meaning the ball can push me back or push my energy back towards this direction. So it will be trying to, as I'm dragging it towards this side, then the energy gained by this ball is trying to push it back towards that, because it should attract to this side. Now if it's moving in that direction, so the energy here, the energy at this point, that is UA, and the energy at this point UB, will give me the potential difference. Now potential difference here can be UA minus UB. So now the one we are now talking about is the gravitational potential. So that is why I said is the energy possessed or acquired by an object due to a change, like from A to B. So due to a change in its position when it is present in gravitational field. So it can be said that gravitational potential energy is an energy that is related to gravitational force or to gravity. So in addition, the gravitational potential is defined. The gravitational potential is defined as the amount of work. So that means gravitational potential now, we represent it as V, is defined as the amount of work required to get a body of unit mass from infinity to the point where potential must be calculated, meaning is the energy divided by mass. So that means gravitational potential is energy or work done from infinity to a point. What is that to infinity to a point? So I said if I have a mass, a ball of mass m, and I have gravitational field around it, and I have a small mass in the field. So if I change the direction of this object to this side, now the radius is small. But if the radius is large, as in infinite, so that means if the radius is infinite, now to take the object back from that infinite to this point, to take it back from infinite to this point, is gravitational potential. So that's why I said that gravitational potential is defined as the amount of work to get a body of unit mass from infinity to the point where potential must be calculated. So the work done in taking this ball, or the work done this ball will possess taking, going back from the infinite position to this point, is gravitational potential. So that work done is what I represent as U, yeah, or the energy. So formally now I can say gravitational potential V is equals to work done in bringing a body from infinity divided by mass of the body. So note that gravitational potential energy is equals to mgdh. Take notes. But this one is gravitational potential. It is the work done in bringing a body from infinity divided by mass of the body. So that means gravitational potential, unit of work done is joule, over unit of mass is kilogram. So in which I can write this as joule per kilogram. So like this. So that means the statement for the C part is correct. So that is true. Joule per kilogram. So it's true. So the C part is true. Now let's say the D. Pressure. What is pressure? we know that pressure is equals to force over area. We know that force is mass times acceleration over area. So mass is kilogram, acceleration is meter per second square, area is meter square. You know that meter will cancel out, so this will be kilogram kilogram times 1 over meter times 1 over s square. So that means this will be kilogram m raised to power minus 1 s raised to power minus 2, because this is per here and it's the same thing as 1 over s square. So if 1 m go here and 1 is here, it will be 1 over m. So that means we have kilogram m raised to power minus 1 s raised to power minus 2. So that means it's also true. The statement is true, is tally with this. So now another one, E, specific latent heat. Specific latent heat. So first, what do you understand by specific latent heat in brief? So the specific latent heat, E, the specific latent heat of a substance is the amount of energy needed to change the states of 1 kilogram of the substance without changing its temperature. The specific latent heat is, we represent it as L, and we know that L will be equals to Q over M, because Q is equals to ml, as in, you remember this in latent heat. So that means L is Q over M. So Q is charges, so while M is mass. So if you look at it now, so specific latent heat here should be, and this one is quantity of it, so it should be joule. The unit should be joule. Then mass is in kilogram. So if I change this should be joule per kilogram. But if you look at what we have in question, what we have here is joule per kilogram per Kelvin, and this is for specific heat capacity. So that means the statement is not true. For latent heat is joule per kilogram. So that means that statement is false. So that E is false. E is false. The answer should be joule per kilogram. Why this one that is false also should be joule per second, like that. So now F, density. What is density? Density is mass over volume. What is mass? Mass is in kilogram. Volume is in meter cube. So if we combine the two, that is kilogram per meter cube. So that means it's correct. The statement is true. Now G, electric modulus. Now what do you understand by electric modulus? We have modular stress. It is stress over strain, in short. So in order not to waste time, because we can take all this as a fresh topic, so electric modulus is stress over strain. Electric modulus. What is stress? We know that stress is force over area. I'm saying force is stress elastic modular, rather I'm saying electric modular, sorry. So elastic modulus is, let me say, elastic modulus is stress over strain. So this is for G, stress over strain. And what is stress? Stress is force over area, while strain is the L over L, change in length over length. If I combine it, stress is force over area, while strain, change in length over length. Now force is in Newton, area is in meter square, the change in length is in meter, length is also in meter. That means this one will cancel out. So that means strain is dimensionless. So that means it will remain Newton per meter square over 1, which is the same thing as n m raised to power minus 2. Or because from here, n Newton per meter square, we can change it to Newton meter raised to power minus 2. But if we check what we have here, is Newton meter raised to power minus 1. So it should be Newton meter raised to power minus 2. So that means the statement is false. So G is false. So it should be Newton meter raised to power minus 2. Now the next one is electric field. Now electric field. Ish. What is electric field? So the electric field is what you can say like the strength of an electric field at any point. So may be defined as the electric or coulomb force exerted per unit positive electric charge at that point. So that means in short, I can say electric field E is force over charge. Now what is force? Force is in Newton, charge is in coulomb. So if you combine, that will be Newton per coulomb. That means if you compare, the statement is true. So H. Now I is a potential difference. So potential difference is of we can represent potential difference, the one you know, that is V equals to IR. Also I, so note that Joule is a unit of work. So and coulomb is the unit for charge. So the potential is defined as the ratio of work. The potential is defined as the ratio of work done to the charge. And the unit of potential difference here is volts. That means if we go by this definition here, that means the potential difference here, work done is in joule and quantity of charge is in coulomb. So that means the statement is true because this can be joule per coulomb. So it is true. That means volts can also be joule per coulomb, or which is also volts. Now the last one, J, resistivity. Now resistivity is common. So J resistivity, we represent it as rho. Resistivity, we represent it like as the symbol rho, which is equals to Ra over L, where R is resistance, A is area, and L is length. So if R is resistance, the unit for resistance is ohm. Then A is area, is meter square. Length is meter. So if meter cancel out, it will remain ohm meter. So that means the resistivity should be ohm meter. So the statement is false. So the correct one should be ohm meter, not ohm per meter. So it's wrong. So that means we are true with this question also. So we'll do more question in other in another video. So thank you.